Welcome to mathematical physics. Have you ever looked at a complex graph and wondered how to predict its peaks, valleys, and curves without plotting every single point manually? Today, we are going to learn how calculus acts as a mathematical compass and X-ray, allowing us to interpret and sketch any graph perfectly. Let us dive in. To begin our journey, imagine you are hiking up a massive mountain range. As you climb, the path is steep, but at the very peak, the ground is perfectly flat for a brief moment before you head down. Calculus gives us a brilliant way to describe this physical experience using the first derivative. In physics, finding these maximum or minimum values is crucial for optimization, like finding the maximum height of a thrown ball. The first derivative tells us exactly how steep a graph is at any single point, acting as a compass that shows if we are heading uphill, downhill, or resting at a flat peak. Now that we understand what the first derivative represents conceptually, let us look at its mathematical form. The formula shows the derivative operator, d by dx, applied to our original function, f of x. This operation produces a brand new function, f prime of x. Think of f of x as the height of a ball, and f prime of x as the rate at which that height is changing. If f prime of x is positive, the graph is rising. If it is negative, the graph is falling. And if it is exactly 0, we have found a critical point where the graph is temporarily flat, signaling a potential peak or valley. Before we move on, let us see this with a concrete example. We are given a quadratic function, x squared minus 4x plus 3, and we want to find where its graph is perfectly flat. To do this, we apply the power rule to find the first derivative, which gives us 2x minus 4. The constant 3 disappears because its rate of change is 0. To find the flat spot, we set this derivative equal to 0. Solving this simple linear equation gives us x equals 2. This means at exactly x equals 2, the slope of the graph vanishes. But is this a peak or a valley? So we have proven that a critical point exists at x equals 2. This brings us to testing the surrounding regions to see if it is a minimum or maximum. We need to check the sign of our derivative on either side of this point. Let us pick a number less than 2, say 0, and plug it into our derivative function. We get -4. Because this result is negative, it tells us definitively that the original graph is going downhill or decreasing as we approach x equals 2 from the left. Continuing our analysis, let us now test a point on the right side of our critical point. We choose a number greater than 2, like 3. Plugging 3 into our derivative gives us +2. Since this is positive, the graph is now going uphill or increasing. Think about the physical shape this creates. The path goes down, hits a flat spot at x equals 2, and then goes back up. Therefore, we have mathematically proven that x equals 2 must be the absolute bottom of a valley, which we call a local minimum. Now that we have calculated the slopes, let us look at the actual graph of our function. Notice the horizontal x-axis and vertical y-axis. The black curve is our parabola. On the left side, where x is less than 2, you can see the blue arrow indicating the graph is falling, just as our negative derivative predicted. At exactly x equals 2, there is a green dashed line representing the perfectly horizontal tangent line where the slope is 0. Finally, on the right side, the red arrow shows the graph rising. The math perfectly matches the visual reality. Now that we know how to find if a graph is going up or down, we need to look at how it is bending. Imagine driving a fast car along a winding mountain road. Sometimes you turn the steering wheel left, making a curve that opens up like a giant smile. Other times, you turn right, making a frown. The first derivative tells us if we are going north or south, but it does not tell us how the road is bending. To understand this curvature, we need the second derivative. In physics, if the first derivative is velocity, the second derivative is acceleration, telling us if an object is speeding up or slowing down. This concept leads us to the mathematical formula for the second derivative. The symbol d squared by dx squared means we apply the derivative operation twice in a row to our original function. Essentially, we are taking the derivative of the first derivative. We denote this as f double prime of x. It tells us how fast the slope itself is changing. If this value is a large positive number, the slope is increasing rapidly, creating a sharp upward curve, or concave up. If it is negative, the slope is decreasing, forcing the graph to bend downwards, or concave down. Let us apply this new tool to a cubic function, x cubed minus 6x squared plus 9. We want to find its inflection points, which are the exact moments where the bending direction completely changes. First, we use the power rule to find the first derivative, giving us 3x squared minus 12x plus 9. Next, we take the derivative of that result to find the second derivative, which simplifies to 6x minus 12. To find where the concavity flips, we set this second derivative equal to 0. Solving this gives us a final answer of x equals 2. Now that we have found our potential inflection point at x equals 2, let us prove how the shape changes around it. We test a point less than 2, like 0, by plugging it into our second derivative. We get negative 12. Because this is negative, the graph is concave down, spilling water like an umbrella before x equals 2. Next, we test a point greater than 2, like 3. This gives us positive 6. Since this is positive, the graph is concave up, holding water like a cup after x equals 2. The point x equals 2 is exactly where the curve changes its fundamental shape. We have covered a lot of ground today. Let us review the most important ideas. The first derivative is your ultimate tool for understanding direction, telling you exactly where a function is climbing or falling. By finding where it equals 0, you can pinpoint absolute peaks and valleys. The second derivative goes deeper, acting as a mathematical X-ray that reveals the underlying curvature and structural bending of the graph. Together, these two derivatives give you a complete, powerful toolkit to sketch and interpret any mathematical graph perfectly. You have now mastered the art of reading the hidden stories told by curves.